All right, so I am recording and the voice is good. I got everything set up. What we'll do today is continue to talk about base conversion. And I hope you guys still remember what we talked about last time because today's lab is about, guess what? Base conversion. Okay. So now we are gonna, let me see if I can refresh your memory, okay? Because, one thing you can do is to watch the video from the previous class, especially after a weekend, because, that's like 5 days and most people cannot really remember everything that we talked about. So it's always useful to kind of watch the video from the previous class to bring yourself kind of up to date, so that you know the context of this particular class. All right, so we'll go ahead and start with some exercises. Okay, so I want you guys to at least try to participate and kind of work on the math as I work out the math. So we'll go ahead and start with a number in base 7. Okay, of all the bases, we're gonna start with base 7. Who would use base 7? So we have 351 in base 7 as a number. And I want to know what is the value of this number in base 10. So I'm going to write here equals to what in base 10. All right. So I'm not sure how much you can remember, but the most fundamental part of this entire discussion is what is a number. Okay? What is each digit representing in a number? 351 is a number. It is in base 7. It is nonetheless a number. So can somebody remind me what is the job of a digit in a number? It gives, well, a name to a value. That's what the entire number is about. But each digit in the number is telling us the quantity of the base to the power of the position of the digit. Okay, so let's think about that for a moment, okay? Every digit in a number, okay. So what is a digit in a number? You're staring at a number. Can someone tell me what three digits are in that number? So we have one, we have five, and then we have three as the digits of the base 7 number. Is that okay? All right, cool. So now we have to name the digits. There's a digit 0, there's a digit 1, there's a digit 2. Who is digit 0? Yep, that is correct. Okay, so this is digit 0. And which one do you think is digit 1? Go ahead. Yep, this is digit 1, and now this is digit 2. Okay, so now we have a way to name each individual digit in a number. Okay, D0 is digit 0, the D1 is digit 1, and D2 is digit 2. What what are they telling us? This is a base 7 number. So the value of this number is whatever D0 is, what do I multiply to D0? Yep. So it will be 7 to the power that is corresponding to the position of the digit. So that means the multiplier to digit 0 is 7 to the power of 0. What about digit 1? Well, it has to be multiplied to 7 to the power of 1. What about digit 2? It is 2, digit 2 has to be multiplied to 7 to the power of 2. When you add up these numbers, that is the value being represented by the base 7 number. Is that okay? All right. So if this seems like a new concept to you, you might need to study a little bit more and review the material from last week a little bit more because this is not new, should not be new to us. Now, did I use base 7 last week? No, I remember that. Okay, I did not use base 7. I used base 2. Does that matter? Should that matter? Nope, because how we read a number is independent of the base. The only thing the base is going to change is what is raised to the power of 0 when we multiply that to digit 0. What is raised to the power of 1 when we multiply that to digit 1, and so on. Okay? So we can use base 7, we can use base 5, we can use base 6. It does not matter. Okay? The interpretation is the same because fundamentally, how we represent a value using a number does not matter. Okay? Because the structure of a number is basically what we are seeing here, independent of the base. Okay, so in this case, we just have to figure out D0 is a 1, so we multiply the 1 to 7 to the power of 0, which is 1, but we'll deal with that later. And then we have 5 times 7 to the power of 1, because digit 1 is 5. And then finally, we have digit 3, or digit 2, which is a 3 times 7 to the power of 2. And then, this is 7, this is 35, and this one is a little harder, but not too hard, 147. And then you just add up all three, 40 to 180. No, wait. Okay, I'll do it step by step because my math is bad here. 147, that is 149. Or did I mess up in my math? Ah, that's right. Okay, thank you. So that's a 36 and 180. Oops. Yeah, 183. Did I do the math wrong again? 189? Okay. Let me redo the math. Okay. I know where I am still correct, which is here. So we're gonna redo it from here. 1 times 7 to the power of 0 is just 1 because 7 to the power of 0 is 1. Thank you. And then 5 times 7 to the power of 1 is 5 times 7, which is a 35. And then 3 times 7 squared is a 49. That's 150 minus 3, which is 147. Are we good so far? Am I okay so far in terms of the arithmetic? So this is 36 plus 147, which is 183. Yeah, so 183 should be the correct answer, which is re-emphasizing this is in base 10. Are we doing okay so far with this example? All right. Yep, go ahead. Well, not necessarily, unless you're also very good, like intuitively good with working with the math in a different base. Yep. Recursively divide by 7? Divide what by 7? But how do you divide 351 in base 7 by 7? Division is not going to get you anywhere. And division in base 7 is very foreign to us. If you have to think about division, you have to first master multiplication. The multiplication table in base 7 is completely foreign to us. None of us has that table in our head, not even me. It doesn't. Okay, if you want to recursively divide by 7, you are turning 183, which is a value already in base 10, back into a base 7 number. that is what division is going to get you. Is that okay? All right. Well, since you mentioned that, let's go ahead and do that. Okay. But before we move on, do we have any questions about this particular slide? If I give you a number in a particular base and I ask you about the base 10 representation of that value, do you know what to do to get that answer? Okay, I get some thumbs up, some nods. Okay, all right, so we are ready to move on. So the opposite is if I give you a value already in base 10, so most values are provided in base 10 because we are used to base 10 already. Okay, so that's native to us. So let's say I'm just picking a number out of thin air. Let's say we have 425 as a base 10 number. At this time, I want to convert it into a base 6 number. Okay, just so that it's not boring. It's every time everything is base 7. I want to convert it to base 6. In other words, I'm asking this is equal to what in base 6? So there are a few ways to do this. You can go for the very systematic way, which is division. You can also go with the less systematic but more intuitive way, which is just listing all the powers of 6, and then you ask, how many do we have of this? How many do we have of this? And so on. Now you end up doing basically the same thing. It is just the process looks a little bit different. Which one do you want me to proceed with? Do you want me to do the uh, repeat repetitive division approach, which is kind of more structured and it is easier to turn into a program? Or do you want to go with a more intuitive approach, which has to do with, oh, we just need to figure out how many 6 to the power of 0, how many 6 to the power of 1, and so on? Which one do you want? The first one? Okay, how many people want the first one? And how many people want the second one? I think the first one has it. Okay, so we'll do the first one first, and then we'll still do the second one. Okay, so I'll cover both. It's just a matter of ordering. Okay, first method, which is repetitively doing a division. So to do this method, I use this notation, which is the 425 divided by 6. This works only if your math is good, okay? Because you're not using the long division, which means you kind of have to keep track of, the whole division thing in your head. I think it's simple enough that we can do this. 7 times 6 is 42. 0 times 6, because 5 is less than 6. So with a remainder of 5, then you divide 70 by 6, which is a 1, and then we have 1 0, so 1 1 with a remainder of 4. And then you divide 11 by 6, which is a 1 with a remainder of 5. Now, we can stop here already, but I can keep going if I wanted to, okay? Because if I wanted to keep going on to divide everything by 6, okay, that's a 0 with a remainder of 1. Divided by 6, it is a 0 with a remainder of 0, and so on, right? Okay, so any additional division by 6 is not going to give me anything particularly useful, just a bunch of more zeros. Okay, is that okay? Does everybody understand the method? Okay, so now the question is, which one is digit 0 in base 6? And which one is digit 1, and which one is digit 2, and so on? What do you think? Oops, my computer just went to sleep because I talked too much. Come on, wake up. Oh, but I think it wanted to go to sleep. It decided to go to sleep. And the most important part is it is still recording. Okay, very good. And unfortunately, what I typed was not recorded. Oh, you guys cannot see the project. Cannot see the. You were able to see it, right? That's the tablet. I think when power went out, or when it wanted to sleep, we lost connection to the tablet. Just have to put it back here. There we go. All right. So which one is digit zero? Okay, I'll give you two choices. This is digit zero, or this is digit zero. The five is the digit zero. Yep, it is the least significant digit. So using this method, after conversion, this is our digit zero, digit one, digit two, digit three, digit four, digit five, and you can see that if I continue the process, we'll have digit six also being a zero, digit seven also being a zero, and so on. In fact, that is a clue of trying to figure out which one is digit zero. Okay, because digit zero should not be affected by continuing to divide whatever is left over by six. So that's a clue to tell us that, oh, okay, digit zero has to be this one. So that's the first method. Second method, okay, so we are moving on to the second method. The second method is a little bit more intuitive. The first thing we do is we say, okay, what is 6 to the power of 0? It is 1. 6 to the power of 1 is 6. 6 to the power of 2 is 36. 6 to the power of 3 is 218, I think. 16? Okay. 216, and that's all we need, okay? So with this method, remember when we look at a number, we are asking, so if we need to figure out this number in basics, and we have figured out that, it only has up to D3 in this case, because this is D0, D1, D2, and then this is D3, and this is in basics, and we want this whole thing to equal to 425 in base 10, then you work with D3 first. You ask, in 425, how many 216s do we have? One. Very good. Okay, so we put a 1 here. So now we go like, okay, 425 divided by 1 times 216. There's a 9, 109 left. So now you say, with the remaining portion, which is 109, how many 36 do we have here? No. Well, actually, hmm, if the two base conversions are different, then we have a problem. There should be three, right? But if this is three, that means my other base conversion is wrong. So did I make a mistake? Well, let's check. It is entirely possible that I make a mistake here. 70 divided by 6 is 11 with a 4 as a remainder. 11 divided by 6 is a 1 with 5 as a remainder. So that is not wrong. And the mistake is here. This is 209, not 109. It's my arithmetics is always getting me. Sorry about that. Ah, I did the palm thing and then it switched to a different screen. But I think that's the screen that we want. Yep. Okay. This is supposed to be a 2. I apologize for my arithmetic, and somehow it is not showing. Okay. Why is that? Okay, that's supposed to be a 2. Okay. Now it's better. Okay, but I'm turning a mistake into a teaching moment. Okay, most people do that when their child is making a mistake and they go like, "Oh, this is great. It's a teaching moment." I do it when I make a mistake. It is also a teaching moment. So what do you think this teaching moment is about? Okay, one, okay, fine, I will admit, use a calculator, okay, check your arithmetic sucks. Okay, fine, that's one. Two, what is it? I can double check my work. Okay, I can detect that there is a problem as early as what I did a little bit earlier, because when I said, oh, this is supposed to be like a 3, it's like, wait, it's not supposed to be a 3. These two are different when they're supposed to be the same. So I must have made a mistake one way or the other, or both. That is possible as well. But something is not right. And that's what prompted me to go back to check my math. I checked the math on the left hand side. They seem to be right. So it has to be math on the right hand side. So I go like, okay, this is the only part where I did some calculation and that turned out to be wrong. Okay, so it is the ability to apply what you have learned to double check to make sure that things are consistent. That is important. Okay, now I'm not expecting you to be able to do it because you're still learning this stuff, but I'm kind of demonstrating that once you understand this stuff here, then you can apply that technique. It's like, wait, something is not right. Okay, all right, so now we have 209 divided by 36. And I think that's a 5 because 5 times 36 is 180, and 180 is 29 away from, um, yeah, with a remainder of 29. So I think that is correct. Okay, because once we have a remainder that is more than 36 or at least 36, then we have a problem. So there's a 5 here. So that means now we are subtracting 180, which is 5 times 36. So this time we have a 9, we have a 2, we have a 29. So now with a 29, we are asking, we are trying to fill the spot of D1, which is asking how many 6 can we fit into 29? So 29 divided by 6 is a 4, okay? And so we have a 4 here. So 4 times 6 is 24. And then finally, we have a remainder of 5, which you can kind of ask to if you want to, because now we're asking how many 6 to the power of 0, which is a 1, can we fit into a 5? Well, the answer is 5. Okay, so these are the two methods. The one to the left-hand side is more systematic because it's just dividing. The one on the right-hand side is not as structured, but it is more intuitive because it really goes back to ask what is each digit in basics trying to tell us. Okay, the quantity of 2 to the power of 2 of 3, the quantity of 2 to the power of 2, the quantity of 6 to the power of 1, and the quantity of 6 to the power of 0. So I misspoke a little bit earlier. These are all in powers of 6, not 2, because we're working with base 6 here. Are we still doing okay so far? So both of these is a result of the fundamental, which is how do we use a number, which is basically a sequence of digits to represent a value. Are we? Yes, go ahead. 180 comes from 5 times 18, 5 times 36, that is correct. 5 times 6 to the power of 2. So the 216 is coming from 1 times 6 to the power of 3. This is coming from 5 times 6 to the power of 2. This is coming from 4 times 6 to the power of 1. And then finally, the leftover is 5 times 6 to the power of 0. Because once we fill in a digit here, then the remaining value that we have to convert to basics is less than what it used to be. Another way to look at this, okay, which I'm not going to document, using the tablet, is to think about a really strange currency system where you have $1 bills, $6 bills, $36 bills, $216 bills, and so on. Okay. In other words, the amounts of the dollar bills are always a power of 6. The amount that you need to make change for is 1,545 in decimal. Oops, I take it back. Forget, forget that. The amount is $425, and you need to figure out, okay, um, what is the number of each denomination do I need to make up for $425? So the answer is one of the $216 bill, five of the $36 bill, four of the $6 bill, and five of the $1 bill. So that's another way to look at this. Okay. And this is also why, and when I mentioned this the first time last Thursday, I said if you know how to make change, at you're working at McDonald's, you already know more than what you need for base conversion. Because I also demonstrated last week there's no regularity as the multiplier to go from one denomination to another denomination. The one that get me the most is from a dime to a quarter because the multiplier in that case is how do you get from a dime to a quarter? What is the multiplication to get there? 2.5, which is not even an integer. Okay, and yet we can do it, right? You guys can figure out, okay, you have, I need to make change for $17.61. Okay, one $10 bill, one $5 bill, two $1 bills, two quarters, one dime, and one penny. That is much more complex than what we are doing here. It's just that you have done it so many times that you go like, well, that's easy. Okay, using the currency system is easy because you have done it so many times. Using basics, you go like, ew, because it is foreign. It's just because you have not done it very often. But the principle of doing this is actually much simpler compared to the currency system because there's no need to memorize. Okay, from a penny we go to a nickel, which is times five. From a nickel to a dime, we have to times two. From a dime to a quarter, we times two and a half. And then from a quarter to a dollar, we times four. There's no regularity right there. Okay, so I hope you guys kind of remember that. Okay, so once we are done with this, we go like, well, do we have any type of equation that can help? Because I like equations because equations is a way to generalize. And generalization is what programming is all about. Okay, you're trying to notice a pattern, and then you're trying to figure out, okay, do we have a universal solution to solve this problem? And the answer is yes, there is a universal solution to solve all of these problems. So I hope most of you have read this entire module over the weekend, okay? Because that is kind of my assumption. If you want to be successful in college, especially after you transfer to a four-year university, you will have to read before class, okay? Because most people cannot absorb all the material just from attending the lecture. Now, I did say most people, which means I would say 90% of the people probably cannot absorb every bit of information just from attending the lecture. The other 10% may be able to do it. Okay, so if you're not taking notes, if you're not reading ahead of time, then you have to think about, am I in the 90 percentile? Am I in the 95 percentile? Because if you think you may not be in the 90 percentile or the 95 percentile, it is usually better to be safe and try to read ahead of time and also take notes during class. Okay. All right, so I'm going to skip some of the material that we have already covered, and instead I'm going to switch all the way to this equation here. Not you, well, it is an equation, but on the right-hand side of the equation is a formula. So then now the question is, what does each symbol mean? What is D of I? What is B? And what is I doing here? And what is V? Well, those questions can all be answered by reading the notes first. Okay? So can somebody tell me? I mean, you can read it right now. Okay? So what is D of I? Oh, first of all, what is, yeah, go ahead. Is digit I. So I is the position of the digit, and then D of I just means, okay, what is the value of the digit at that position? Is that okay? And what can be a value of I? Well, I has to be an integer because it is a position. but it can go as negative as you want, and it can also go as positive as you want. Okay, because each number is intrinsically it has an infinite number of digits. Then you go like, no, tech, that is not true because you look at this here. Okay, so I'm just switching back here. We'll just take a look at 425. Okay, so you look at 425 and you go like, see, there are only three digits here. Yeah, oh, I beg to differ. Okay, so we'll rewrite 425 here. I go like, I can always do this, right? And again, and again, and again, and again, and again, and so on. So, so that means every number intrinsically has an infinite number of digits. It's just that we only have a few that are non-zeros. Does that make sense? So when we are trying to make a certain equation to account for, okay, what is the value being represented by a number? I'm just going to go like, well, we'll just kind of go all the way to positive infinity as an integer. What about the negative side? Well, that's digit -1. Turns out to be 0. Digit -2, which is also a 0. And I can append as many zeros as I want to the right-hand side, of the decimal point here, and it wouldn't change the value being represented. So that means all of these digits are actually here. But because they're all zeros, I'm just not wasting my time to write them. Does that make sense? So that's why when we look at the sigma or the summation, it starts from negative infinity right here. So I is an integer that starts way negative to way positive. It is just a position. D of I, which is the actual value, the actual digit at position I, is specifying a quantity. What, whose quantity am I specifying? It is specifying the quantity of, what do you think B is representing? The base, exactly. So it's representing how many base to the power of I do I have. So that is the structure of how we interpret a number in base B, and this is how we figure out the value being represented by that number. Are we good so far? All right, cool. So we can also have a general equation to go backwards, okay? So I'm going to skip the rationale to talk about that and jump all the way to the equation itself. So this is going the opposite way. You give me a value, you give me the base. I will tell you what digit I, and you give me the digit position, which is I, and I'll tell you what digit I is supposed to be. Okay? Hmm. Well, looks like we can test this, right? Because the example that I just gave you, okay, the one that we just worked out, is perfect to test this particular thing. In other words, we already know that V is 425. That's what is given to you. We already know B is 6 because we were converting to base 6. The only question that I need to ask you is which digit do you want me to figure out? Because this equation can only figure out one digit at a time. Okay, so you guys can give me that question. So I just need to know which digit you want me to convert to. Which digit do you want me to figure out? We know value is 425. We know the base is 6. And I just need you to tell me which I do you want me to work out. 3? Okay, sure. We can do 3. Okay. So the equation says d of 3 is v, which is 425, divided by, if I remember right, the base, which is 6, raised to the power of the digit position, which is 3. And then you take the floor of that, okay? And then you mod, after you do all this, you do a mod with the base, which is also 6. Okay. Um, I have never seen this symbol before. The floor symbol, I have never seen this before. Well, that means that person has not read the notes. Okay, so what is the floor? Okay, I'll explain it here and then we'll switch back to the notes. The floor of X is the largest integer that is, um, I have to remember this is whether this is correct. I think it is. That is less than or equal to X. There we go. I think that is the correct one. Well, we'll figure this out. Okay. So tell me what is the floor of 1.6? Okay, so let's interpret this, okay? What is the largest integer that is still less than or equal to 1.6 in this case? 1, okay? Does that make sense to you? All right. So that's what floor is. So when x is non-negative, then the floor is basically just getting rid of all the decimal points. It is the same as truncation, okay? Now, if x is negative, it is not truncation, okay? Because you have to round down, okay? In that case, yes. Say that one more time. Is floor? I would not use the word round because round has a different meaning. I would use exactly this to describe floor, which is you're finding out the largest integer that is less than or equal to the thing that you're flooring. It's not exactly truncation, okay? Because I refrain to use the word truncation because what do you think is this? Okay, let's think about this. Okay, let's think about this. What is the largest integer that is the most important part here is less than or equal to negative 2.1? It's negative 3. Okay, so in this case, it is not, it doesn't look like truncation to me. Because truncation means we're just getting rid of the decimal point and everything to the right hand side of the decimal point. But that's not floor is. But most of the time in this class, we don't take the floor of a negative value. So something like this, taking the floor of negative 2.1 usually does not happen in this class. But it is still important to differentiate between the floor of something versus the truncation of something. They are still the same for non-negative values, but then for negative values, they are not the same thing. They are defined differently. All right, so let's go back and try to figure out all the math here. So we have 425 divided by 216. So we have a 1 of 216, and then we have a 9 here, and a 0 and a 2 here. So we have none of that. Oh, what am I doing here? We have a 1 here with a remainder of 209. So that means, the actual result of this division, 425 divided by 6 to the power of 3, is 1 point some blah, blah, blah. You go like, Tag, aren't you going to figure out what that point blah, blah, blah is? I don't have to. Because when you take the floor of 1 point blah, 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 it is just 1. So we have 1, being this part here. 1 mod 6 is, okay, what is mod? One is the mod is the remainder of the division. So we have 1 divided by 6, but I don't care about the quotient, which is a 0. I only want to know what is the remainder of 1 divided by 6. What is that? No. Oh, you guys need to go back to elementary school. It is 1. The remainder of 1 divided by 6 is 1. Okay, that's okay, but I'm still gonna do it. I'm still gonna say something about it. I have 1 candy, and there are 6 children in front of me. I have to distribute the candy evenly as a whole number. So what do I end up doing? Nobody gets a candy. and that is the remainder. I keep the candy in my pocket. So 1 divided by 6 has a quotient of 0, which means nobody gets a candy among the 6, but the remainder is 1 because, huh, I get to pocket that 1 candy back. Is that okay? All right. Sometimes the boundary cases of simple things are actually difficult to perceive or to understand. This is one of those cases. It's like, if I ask you, what is 13 divided by 6 and what is the remainder of that, you guys go like, oh, it's 1, easy, okay? But 1 divided by 6, what is the remainder? That is actually a little bit trickier compared to, a larger number, divided by 6, or the remainder of a larger number divided by 6. All right. So are we okay with this equation? What it does and when to use it. So there are two equations. One will give you the value represented by a number in a particular base, probably not 10, okay? That's the earlier one. This one will give you a single digit when you are given a value, which is usually in base 10 already, a base, and also a position, which is where the position of the digit that we are trying to figure out. That's okay. Take your time. That's okay. These seats they're not really designed for people. Yep. To do what? To convert a known value into a different base, or to convert a number in a particular base back into a value that we are familiar with. Yeah. Okay. I see what you mean. So if it depends on whether you want the most optimal way to do it. This way is not optimal because you ended up doing repetitive calculations. So the repeated division one is the most optimal. The way C++ handles division is not optimal because you need to get the quotient so that you can keep dividing, but at the same time you also need to extract the remainder because that is the digit of the new base. But C does not give you both at the same time. It will give you the quotient if you use slash, and it will give you the remainder if you use percent, right? Then you're still multiplying, you're still wasting processing time. So the funny thing is the processor, the Intel, AMD, any modern processor, if you ask it to do division, it actually gives you both the quotient and the remainder at the same time. So there's no actual really, really efficient way to do it in C and C++ because there's no way to get both the remainder and the quotient at the same time. But that method turns out to be as close as you can get being the most efficient way to do things. But it is still not the most efficient way just because the language does not give you the remainder and the quotient at the same time, even though the processor does. Yeah, in assembly it does. Yep. All right. So that's a good question. And that pretty much concludes your base conversion. And let me switch back to my notes here. Okay, what about base 2? It's easy. B is 2, the base is 2 in this equation here. So that's, kind of what that is. So now we ask, how are values represented in a computer? In a computer, after all, it computes in order to compute, it has to store values before and after the computation. So everything inside the computer is in base 2. In other words, if you look into the memory of a computer, the only thing it can store are zeros and ones. Then you go like, well, I think it can store my name and it's not zeros and ones. You go like, how does that happen? Okay, how does it represent the uppercase T of my name and the lowercase a and the lowercase k? It stores it as a number value, and exactly, it is coded as a number. Okay, and that particular coding standard is called ASCII, which is American Standard for Information Standard Code. Okay, American Standard Code for Information Interchange. That's ASCII. But we came this close of using a different standard to encode characters or encoding letters and punctuations. It's called EBCDIC. And of course, in this class, nobody remembers EBCDIC or know what EBCDIC is. If you have a grandparent who used to program mainframe computers, your grandparent will basically spend hours and hours to talk to you about, oh yeah, I remember EBCDIC, because EBCDIC is derived from BCD, which is binary coded decimal. So EBCDIC is the full name of EBCDIC is something that is okay. Let me see if I can still figure that out. Not that it is truly relevant for this class. And I have misplaced my pen, my stylus. Where did I put it? Ah, right here. Okay. So EBCDIC is EBCDIC. I think. I think this is extended binary coded decimal. I cannot remember the IC. Obviously, a Google search will quickly find that out. Interchange code. I wouldn't be surprised, but we'll see. EBCDIC. Yep, you're correct. Interchange code. So this is IBM's own way of encoding characters and punctuations into, I think 7 or 8 bits of information. It is a different scheme. It is actually a very ugly one. Um, but we came this close of using EBCDIC instead of ASCII. ASCII is much better. So now, how does ASCII represent any code? Okay, so you just have to look it up. So ASCII that's how it's spelled. It is American Standard Code for Information Interchange. Okay, we talked about that. And then Wikipedia has a page on this. Okay, and let me see what is the best way to look at the actual table. Okay, we can just look at it this way. So the way we look at this is the columns are the most significant 3 bits, and then the rows are the least significant 4 bits. So that means, uppercase T, which is right here, is 101, which is, the column header, followed by the least significant 4 bits, which is 0100. That's, how T, uppercase T, is encoded as an ASCII code. Okay, then you guys go like, well, okay, this is all cool, but with only 7 bits, how many symbols and characters can we encode using only 7 bits, 7 binary digits? So I'm asking you a very indirect question to see whether you can apply what you have learned already just today and also Thursday to figure out the largest integer that you can represent using 7 digits in base 2. Okay, yep. 2 to the power of 7, what? 128, which is 2 to the power of 7, but that's not entirely correct. You guys are so close. Yes, it is 127 because 127 is 2 to the power of 7 minus 1. The minus 1 has to do with we start counting from 0. It's already taking up a spot. There are, in fact, 128 spots, but because the first spot is taken by 0, so that means the last spot is taken by 127 and not 128. Okay, so you guys are close. Okay, good job. So now you go like, okay, so that means we can only represent 127 things, punctuations, uppercase, lowercase, digits, and so on. So now the question is, what about the emojis? I know I can type emoji in text so that the other person actually receives the emoji. What's happening here? It's Unicode, exactly. So Unicode is 16-bit wide. So that means you can have up to 65,536 symbols, in that case. So that's a lot of characters, right? To cover a lot of languages. Yep. ASCII only has 7 bits. In other words, when you transmit text in ASCII, it can only range from 0000000 all the way up to 1111111. So there's no quote unquote extra bit. And that's why earlier modems, typically only transmit in 7 data bits. The one other bit is called the parity bit, which is for error checking. So you're correct, that one extra bit in a byte is for error checking, but the transmission itself only transmits 7 bits at a time. All right. So any other questions about this? Yes. So the space is gradually populated by different languages. So sometimes we basically the ASCII code is also called UT8, UTF8. Okay, and they occupy basically you have all the most significant A bits are zero, and then the least significant A bit would be just the ASCII code. That's how ASCII stands in Unicode. But as we add more languages into ASCII into Unicode, they use up more spaces. But exactly how they allocate and kind of reserve your space, that's up to the um, international committee to kind of do all the math and decide, how to carve up the space of 65,536, representations. And they have even Klingon as a fictional language is in Unicode. Yes, I know you guys will go like, "What are you talking about?" So if you can look it up, Klingon, Unicode. I'm not a real Trekkie. I just know enough to kind of point out these little things. So Klingon use up, one particular, it uses covering 154 modern and historic scripts as well as multiple symbol sets and emoji. Interesting. But Klingon is also in the Unicode realm. Most emojis are too. Smiley face, sad face, they are all, a part of Unicode. Yep. Okay, well, that's an interesting question. I know the answer already, but I want the class to think about it a little bit. So the question is, if Unicode is commonplace and we use Unicode as emoji, various languages and whatnot, how come we cannot use emoji? How come we cannot use Unicode to as a password? Instead, the password typically is only a subset of the ASCII code. Why is that the case? The answer is simple. It has to do with your keyboard. Yeah, well, the way you enter Unicode is typically you enter in the hexadecimal representation. So you have to do a Alt, Shift H or U, I think. Yeah, yeah, but my keyboard does not have the numpad, so you have to do a Control or Alt Shift U to put it into Unicode mode, and then you use the hexadecimal digit to spell out the 16 bits of the Unicode, and then you press enter. So I don't think that's a good way to enter my password. Yep. Klingon, angry, must fight. Okay, and all emojis. Yes, I do not know. Alrighty. Okay, so that pretty much concludes the discussion of base conversion. Okay, but the most important part is the fundamentals of how a number represents a value, and the two equations. One equation says if you give me all the digits in a particular base of a number, I will convert it to the value being represented. The other one goes the opposite way. You give me the value, you give me the digits position, you give me the base, I will tell you what value that digit is supposed to be. Okay? So that's basically what your lab is going to be involved in today's lab is really just base conversion in both directions. Okay? Yep. Say again? Nope, this one does not use Logisim. So you get a short break from Logisim. All right. So we still have plenty of time. So we're going to move on to the next module, okay, which is about base 2 addition and subtraction. So we are going to go switch to that module. Okay, let me show you where to find that module. And that is just further down a little bit, which is here. We get to binary addition and subtraction. Okay, open as a new tab. All right. So the first thing about this particular module is how we do things in base 10. In other words, the way the flow goes in this particular module is one, we study how we do things in base 10. Hopefully it is familiar to you. Two, we extract the structure out of how we perform multi-digit base 10 addition. We extract the structure out of it. And then we just generalize the whole thing so that we can do it in any base we want. Then we specialize the approach to just base 2. And then number 4 is, oh, if it is in base 2, we can do all of these special things that we cannot do in other bases. And then at the end of that process, step 5 is, oh, we can do everything using logic gates. And as a result, we can also make the conclusion that we can do everything in transistors because we already know how to use transistors to implement all the logic gates that we are familiar with. So as a result, if I can convert everything to logical NOT, logical and logical OR, then we can do everything using transistors, which is basically what's happening in the computer. Is that okay? So are there any questions about those 5 stages of the discussion? Because understanding the map of how I arrange things can be helpful because otherwise, the transition from one stage to another stage may look confusing. So I just want to make sure that that part does not look confusing so that you have a general map of how this goes. Okay? All right. So now we are going to get started with base 10, okay, multi-digit addition. So I just want to see if you guys still remember how to do it. 219 plus, okay, let's give it to 744. Okay, do you know how to do this? If I see somebody pulling a calculator out, I go like, okay, all right, so how do we get there? Okay, so the way I do it, on paper is, oh, 9 plus 4 is 13, and then 1 plus 4 is 5, 5 plus 1 is 6, And then 2 plus 7, there's no carry from 1 plus 4, so this is a 9. Okay, is that okay? The most important concept in this case is the concept of carry. Okay, so we're going to focus a little bit on the concept of carry. In other words, if I ask you what is 7 plus 6, what is the answer? Most people will say, oh, that's easy. It's 13. Well, that is not wrong. Okay. But if you say 13, it's not going to help in a multi-digit addition like the one that we just carried through. So one way to say the result of 7 plus 6 is it is 3 with a carry of 1. Because the concept of a carry is, in this example, 13 is more than what we can represent using a single digit in base 10. A single digit in base 10 can only represent from 0 to 9. Okay, so 13 is out of that range. So what do we do when a single digit cannot represent, the quantity that we want? Then we go like, well, maybe we just, this particular position, I'll just store the 3. Okay, then you go like, what about the 10? What about, oh, I'll let you deal with the 10. Okay, you just let the next digit to deal with the excess of whatever, quantity that you have to deal with. Is that okay? Okay, all right. All right. So let me give you another example. Okay, so we have 219 again, but this time we multiply that by, put a 7 here, and then put a 8 here, and then we'll just put a barely a 1 over here. Okay, so what do we have? What is happening in this case? 9 plus 1 is a 0 with a carry of 1. 1 plus 8 is fine. It's just 9. But hold on, we have a carry from the earlier or the right hand column. So now we have 10 again, which is a 0 with a 1 as a carry. So now we have 2 plus 7, which is just 9, which we are good. No, because we have that 1 of a carry. So we have a 0 here again. And we have an overall carry of 1 over here. In other words, this is the result. It is not 1000. It is 000 with an overall carry of a 1. That is how it is going to be represented inside the computer because it is fixed number of digits. The numbers that you're adding and the sum, they must have the same number of digits. Then you go like, but this is wrong then. It is not wrong. The answer is 000 with an overall carry of 1. This overall carry of 1 is really a carry of 1000. So that means we still have 1000 back. It's just not spelled out the way that you're used to. Okay? So are we still doing okay so far? Okay, so the most important part of this example is there are two ways to have a carry. You can have a carry from those given 2 digits to have this carry over here, but you can also have a carry because the entire column, including the carry from the other side, is greater than or equal to 10. So you have another carry over here. So there are two ways to have a carry. Okay? So now this is the part where I do an abstraction, which means I'm extracting the structure of multi-digit addition, into a form so that I can say, okay, generally speaking, this is the way to carry out a multi-digit addition. So it's, quote unquote in base 10. Okay, the base 10 part is easy to deal with. So we'll take a look at how we do things first. I will call this row X, okay? It's one of the numbers that you're given to add. This row is called Y. The other number that you're given with to add, this row is called S, which is the sum, okay? So those we know already, no big deal, okay? So we have X, we have Y, and then we have the sum down here. But then in between, I'm adding two more rows that typically are not represented. This one I call Q. I cannot remember why. This one is called K because these are the carries. Okay, so now we go like, okay, that looks really confusing. Let's go back to our example and see how to make use of this new format. So we'll use the first example, which is 219 plus 744 in base 10. So the Q row is basically what I call the single digit sum of xy. The single digit sum is basically saying if I do not take the carry into consideration, what is the one digit that is corresponding to the position? So 9 plus 4 has a single digit sum of 3. 1 plus 4 has a single digit sum of 5. 2 and 7 has a single digit sum of 9. In other words, I simply ignore the carry. Are we good so far? All right. So what about a k? Well, the k gets a little bit complicated. There's no carry from the previous position because this is the least significant digit, so that is going to be a 0. So when we look at the next position, which is this position here, then we go like, oh, there are two ways to have a carry. Because when we add 9, oops, okay, when we add 9 and 4, that already has a carry. So we say, oh, there's a carry over here. And then when we look at the carry position over here, then we ask, does 1 plus 4 end up with a carry? Nope. Does 5 plus 1 end up with a carry? Nope. Okay, so we do not have a carry over here. Is that okay? All right. So now the sum is once again a single digit sum between the q and the k. So now we have 3 plus 0, which is just a 3. 5 plus 1 is just 6. And then 9 plus 0 is just 9. Okay. So now we move on to the next example. Okay. So we have once again 219 as x, but this time we have 781 as y. So we'll take a look at what is going to be our q, what's going to be our k, and what's going to be our s, the sum. So once we do the same thing again. What is the single digit sum of 9 plus 1? 0, but we don't care about the carry. Okay, so single digit sum only cares about the leftover portion after we take care of the carry. So that's just a 0. What about 1 plus 8? What is the single digit sum of 1 plus 8? 9. 2 plus 7. Okay, very good. Okay, you guys are getting the hang of this. This is a 0 because there are no less significant columns. So this is always a 0. So when we look at this position here, there are two ways for it to have a carry. The 9 plus 1 can give it a carry. The 0 plus 0 can, quote unquote, potentially give it a carry, but obviously it is not going to give it a carry. But nonetheless, it is a carry of 1. So we put a 1 here. And then when we try to figure out this position here, then it also has two chances to get a carry of 1. 1 plus 8 can contribute a carry here, which is not happening, but 9 plus 1 does. Okay, so we still put a 1 over here. And then when we look at this position over here, we have 2 plus 7 that can contribute a 1 here. No, it's not, it doesn't have a carry of 1, but 9 plus 1 does. So we put a carry over here as well. So this is a good time to name the column, to name the column with a digit. This is digit 0, this is digit 1, digit 2, and this is digit 3. So when we compute the sum, we're basically just asking about the single digit sum of 0 plus 0. What is the single digit sum of 0 plus 0? The single digit sum of 9 plus 1? 0. And what is the single digit sum of 9 plus 1? Yep, that's it. Okay. So we now go like, okay, that's kind of interesting. Okay. So now we go like, okay, so that means, when we look at the three-digit thing, we have x2, x1, x0 being digit 0, digit 1, and digit 2 of x, digit 2 of y, digit 1 of y, and a digit 0 of y. And then we end up with q0, q1, and then q2 over here. And then we have k2, and we also have k3 here, k1, and then k0, s2, s1, s0. In other words, all I have done here is to say, let's not work with actual digits. Let's just work with the name of the placeholder of a digit and try to figure out the relationship between the digits. Now, this is probably the most confusing, the most important step, which is abstraction. Okay, I'm trying to abstract what we did with the example into a structure that applies to every 3-digit by 3-digit base 10 addition. So let me pause a little bit here to see if there are any questions about what we are doing with this. Yes. Mm, well, let's take a look at how the k bits are calculated. Okay. So because we're trying to extract the structure. In other words, what I'm really asking is if I need to use a function, we just call it r, and we say, r of uv is the single digit sum of u and v. U has to be a single digit in base 10. V is also a single digit in base 10. So how do we calculate a single digit sum between u and v, knowing that each one is just a single digit in base 10, which means the range of value for u is from 0 to 9. The range of value of v is also just from 0 to 9. I just need this function to tell me what is the single digit sum of u and v. How do you calculate that? Okay, so let's look at some examples. Okay, maybe by using the examples you can figure out the pattern. So R of 6 and 7 is what? What is the single digit sum of 6 plus 7? 3. Okay, very good. R of 6 1, 7. R of 5 5, 0. R of 5 7, 2. Okay, all right. So I think you guys are getting the pattern. So now let's go back to how do we define R of UV in base 10? Okay, I'll give you one clue. It involves mod. Hmm. We just work with these two. These are the parameter names. So what do we do with U and V in order to give us to calculate the single digit sum of UV? Does that work? Yep. Okay. All right. So you can always just kind of plug it into the ones that we have already worked out and go like, oh, okay, that seems to make sense, right? Okay. So now we're gonna work out another one. Yes. Yeah. At this point, it is. Yep. At this point, it is. But the calculation does not even care about whether that's always zero or not. Okay. All right. So that's R. And now we want to define C, which is carry of U and V. In other words, in base 10, U is a single digit, which means it can only go from 0 to 9. V is also a single digit, which also means it can only go from 0 to 9. When we add U and V, I want C to return whether the carry is a 1 or the carry is a 0. Okay? So let's go through the same examples as above. Okay? What is the carry of adding 6 and 7? It's a 1. Okay, very good. The carry of adding 6 and 1. Okay, the carry of adding 5 and 5. Okay, and then the carry of adding 5 and 7. Okay, so you guys are getting the pattern. So now the question is, how do I code this as an expression? I can see two ways to do it. One is kind of expensive, the other one is a little bit obscure. Hmm? Say again? Mod does not get you the answer because mod gives you the remainder, which we have already used up here. Hmm? Mod Nope. Mod is not going to save you. Hmm? Division will save you. Okay, so u plus v divided by 10 will actually give you the correct answer because that division is an integer division, so it works. Okay, but the other way to do this is based on comparison, which is even better. So you look at u plus v. If it is greater than or equal to 10, then we return a 1. Otherwise, we return a 0. Now, if you're looking at this expression and you're frowning, you go like, I have never seen this ever in my life. Well, get used to it. It is called a ternary expression. There are three parts to a ternary expression. Well, does that surprise you? What does TERN mean in ternary? Three, exactly. So there are three parts to this expression. The first part is before or to the left-hand side of the question mark, evaluated like a Boolean value. So it returns either true or false. The middle one, which is between the question mark and the colon, is what you need to what you return when the condition is true. The one to the right-hand side or the last value, or the one to the right-hand side of the colon, is the value that you return when the condition is false. In other words, it is a conditional statement in an expression. If this, then this, else this. It is called a ternary expression. It is a very useful expression, even though most people say, well, isn't it better to use a conditional statement? No, a ternary expression has a lot of uses in programming. So are we doing okay so far with the ternary expression being the answer to this question here? Okay. And we got about 3 minutes, and I think that's just enough time for us to figure this out. So if I generalize and I say, what is, uh, okay, what is Q of I? Using everything that we have defined up here. So I'll give you the answer, okay? So because they're all in the module anyway. So Q of I is the R of xi, yi. And then if I ask you what is S of I, that is R of qi, ki. And then if I ask you what is k of I plus 1, it is c of xi, yi plus c of qi, ki. Now, there's nothing here that is new to us. Okay, I'm just generalizing or abstracting the structure of how we performed base 10 multi-digit addition into a kind of more spelled out format using XYQK, and normally we don't use QK in a normal by hand type of calculation. And then the next step is to say, let's not look at actual digits, okay? Let's just give each digit a name, x0 to x2, y0 to y2, etc. Okay? And then we go like, okay, so the bottom line is, how do we calculate a single digit sum? R does that. How do we know what is the carry? Okay, do we have a carry of 1 or do we have a carry of 0 when we add two single digits? Function C takes care of that. And then what we do is we just use the function R and the function C to relate x and y to q, to relate q and k to s, and then to relate x, y, q, k to k itself. But this k is the next column. Okay, so when you have time, okay, I want you to read the module and try to mentally make connections of all of these things. But of the entire whiteboard, okay, I know you guys are eager to start your lab, but of this entire board here, which part is specific to base 10? Point out to me which part of this entire discussion is specific to base 10. This mentions 10 over here. This mentions 10 over here. So that means if you want to do single digit or if you want to do multi-digit addition, in a different base, what do you need to change? Switch the 10 to whatever base you want to use. So now we have the structure to perform multi-digit addition in any base I choose to. Yes. Okay. So of the entire whiteboard here, or of the entire tablet screen over here, which part is specific to base 10? In other words, it won't work in some other base. But 10 is only mentioned here and here. Those are the only two places that mentions 10. The rest has nothing to do with the base that you're working with, which means it will work in any other base. If I were to switch these two 10 to 2, then I know how to perform addition in base 2. If I switch the 10 to 7, then I know how to do base 7 addition. Okay, so that really is important. And before you guys leave, let me give you the code for the lab today. All right. Okay, mosquito. So the lab today is about base conversion, which is this one here. So I'm going to unhide it, and you need to know the access code to get to it. And the access code is, since we talk about base 7, so the code is heptapod. Because hepta means 7, pod means limbs, so heptapod is a creature with 7 limbs. Where do we find creatures like that? In the movie. Which movie? Arrival. That's it. Yep. All right. I'll catch up with you guys at the lab once I finish packing up here.